Okay, in this video we are going to prove the binomial theorem by induction. So first let us recall what the binomial theorem actually says. So basically what it says is that x plus y to the power n is the sum over k from 0 to n of n upon k times x to the k times y n minus k. And just to recap, this n over k is called the binomial coefficient and is equals to n factorial over k factorial times n minus k factorial. And to recap, n factorial is just n times n minus 1 times n minus 2 and so on, right? All the way down to till we come to 1. So n is a natural number, right? Okay, so let us prove this theorem by induction. So by induction, first what we have to do is we have to prove it by we have to prove the base case. So our base case is for n equals to 0. So let us write base case n is equals to 0. Let us calculate x plus y to the power 0. X plus y to the power 0 is just 1, right? Because any real number to the power 0 is equals to 1. There might be a few exceptions, but since x and y are real numbers, the addition is a real number, and if you exponent that to 0, then you get 1. Okay, now we have to show that the right hand side is also equals to 1. So this, we wonder, is this the same as the sum as k goes from 0 to n, which in this case is 0, n upon k, well, n is 0 here, 0 upon k, x to the k, y to the n minus k, and that's just minus k because n is equals to 0. So this is equals to, we only have one sum in this one over here, so this is equals to 0 upon 0 times x to the power 0, because we substitute for k equals to 0, and y to the power 0. So these both are equals to 1, and that's just 0. The binomial coefficient is just 0 factorial over 0 factorial times 0 factorial. And one of the important properties of the factorial is that 0 factorial is equals to 1. It is most usually defined to be equals to 1. So this is equals to 1, and the base case has been proven, right? So we showed that this binomial theorem, this formula over here, is true for n is equals to 0. Now we do the induction hypothesis. The induction hypothesis is just the theorem itself. It just is, I'm going to copy this. This is just this is our induction hypothesis, right? This is our induction hypothesis, and now we do the induction step. So we showed that it is equals to, that for 0 it is the case. We assume that it is true for x to if the exponent is n, and now we show that it is true for n is equals for n plus 1, right? So the induction step, we have to show that x plus y to the power n plus 1 is the sum as k goes from 0 to n plus 1, n upon k, x to the k, y, n plus 1 minus k, right? Okay, so let us first work out the left hand side. So let us calculate x plus y to the power n plus 1, n plus 1. Well, that's just equals to x plus y to the power n times x plus y, right? And now we can use the induction hypothesis for this guy over here. So we get that this is equals to the sum as k goes from 0 to n, n upon k, x to the power k, y to the power n minus k, and all of that we multiply by x plus y, right? So now what we can do is we can use the distributivity of the real numbers over the multiplication. So this is equals to, we get two sums now. X goes from k to 0 to n, n upon k, and now we multiply x into here. So we get, this is a k and this is an n. So we multiply this whole term by x. So we get x to the power k times x, which is x to the k plus 1, y, n minus k. That is the first term. Right? Now the second term is more or less the same thing, but instead of multiplying with x, we multiply by y. So again, we get the k. So plus k goes from 0 to n upon k, x to the k, y, n plus 1 minus k. Right? So now we have these two terms. Now we somehow want to make this, show that this is equals to the same thing over here. Where is it? The same thing as this. This should be n plus 1. Pardon me. The same thing as this. So let us clean this up a little bit. First of all, what I can do is I can write the first term as the sum from 0 to n minus 1 plus when k is substituted with k. So this is equals to the sum as k goes from 0 to n minus 1, n upon k times x to the k plus 1, yn minus k. And now I just take the same formula inside the sum and substitute n for it, plus n over n, because we substitute k equals n, x to the n plus 1, and when k is equals to n, y to the n minus n is y to the 0 is equals to 1, so n upon n. And remember that this is equals to 1, n upon n is equals to 1. Okay, that's the first term. The second term, I'm going to also split into two sums. Instead of going from 0 to n, I'm first going to take the term where k is equals to 0, and then add the term from 1 to n. So this is equals to the sum as k goes from 1 to n, n upon k, x to the k, yn plus 1 minus k. That's exactly this term, but instead of going from 0 to n, I go from 1 to n, and then I add the term when k is equals to 0. So plus, and now we substitute for k is equals to 0. So we have n upon 0, x to the 0, x to the k is x to the 0 because k is 0, which is equals to 1. And here I get y n plus 1, right? Now there's a small trick which I can do. It's already looking nice, but we can write this in a better way, right? So we can notice that this term here, we have k plus 1, and here we have k. So if we could somehow align these two sums, so make them look similar, then we will have simplified it a lot. So the way to do this is to actually substitute in the first sum k prime is equals to k plus 1, or the other way around is k is equals to k prime minus 1. So I'm just gonna copy all of this. I'm gonna copy all of this, and then we have paste that in here, right? And now I can delete this because n upon n is 0, and n upon 0 is also 1. Sorry, it's 1, not 0. And this is y to the n plus 1, right? And now I'm substituting k prime is k plus 1. So when k is 0, k prime is 1. So this becomes k is equals to 1. And when k is n minus 1, k prime is n. So this is just n. And k is k prime minus 1. So in here I get k prime minus 1. And k plus 1 is k. So that's just k prime. And n minus k becomes n minus k minus 1, which is the same as n plus 1 minus k. N plus 1 minus k, right? And now look here, I've got two sums over here which look very similar. I have a k prime here. The k prime is a dummy variable, right? Because I'm summing over it. So what I can do is this should be k prime here as well, right? So what I can do is I can replace k prime by k So I'm just going to make this k, and similarly here k minus 1, k, right? Okay, now what I can do is, from the last video, if you remember, we proved that n upon k plus n upon k minus 1 is equals to n plus 1 upon k. Okay, this is called Pascal's identity, and I have exactly this here, right? K is equals to 1, right? I have the same sum over here, but I have different coefficients. I have n over n k plus 1 and n over k. But I can use this identity to write these two as n plus 1 over k. N plus 1 over k. So this is equals to the sum as k goes from 1 to n plus 1. Sorry, k goes from 1 to n of n plus 1 over k, x to the k, y to the n plus 1 minus k, right? And then I have plus x to the n plus 1 and plus y to the n plus 1, okay? And now, I'm not completely done yet because I have to still integrate these two terms into the sum in some way. But what we can notice is that x to the n plus 1 is the same as n plus 1 over n plus 1, right? Because n plus 1 upon n plus 1 is 1, and this is n plus 1 over the same as n plus 1 over 0 y n plus 1, which is also equals to 1. So let's write this is equals to 1 and this guy is equals to 1, right? And now I'm almost done because this is just equals to the sum as k goes from 0 to n plus 1, n plus 1 upon k, x to the k, y n plus 1 minus k. Because this term here, this term over here, is just the same thing here for when k is substituted 0, right? And this term is also this term when k is equals to n plus 1. So I can integrate them into this sum and write it in this form. So this completes the induction. So this completes the proof of the binomial theorem by induction. That's it. Okay, please like, share and subscribe to the channel. More content like this is coming up, and I hope to see you in the next video. Thank you. Bye.